All right, we're going to lose one more layer of detail when we go to acceleration view. Let's take a look. So now this is graphing acceleration on the y-axis. And the x-axis is still time. Okay? If you're moving at constant velocity in the positive direction, that means that your velocity is not changing. And remember that acceleration by definition is a change in velocity over a change in time. So if your velocity is not changing, if it's constant, then it means then your acceleration is 0. And so we would show that right here, saying no acceleration. And if you're moving at constant velocity in the negative direction, well, you're still moving at constant velocity, so your acceleration is 0 there as well. So no difference. Notice that you can't tell from these graphs which direction the object is moving. You can only tell that it's moving at constant velocity, right? Here's that removal of some of the detail. If you're speeding up, your velocity now is changing. And if you're speeding up in the positive direction, then your velocity is getting increasingly positive. And if your velocity is getting increasingly positive, then let me just show you a little v versus t graph. So here's velocity versus time. So speeding up in the positive direction would mean that you're going like this. And if you took the slope at each moment in time, right? You took the slope here, and then the slope here, and then the slope here. As long as you're speeding up at a constant rate, then the slope would be consistent. You'd get the same slope 3 times. And so if an acceleration graph is just the slope of a velocity graph, then you could just record the slope. The initial slope would be here, the next slope would be the same, the last slope would be here, and so you'd get constant acceleration, meaning the rate of change of the velocity is constant the whole time. And if you were speeding up in the negative direction, you would get a v versus t graph looking like this. Here's your velocity, here's your time, and I should extend it. Speeding up in the negative direction means that you're going this way, right? And so now you have a consistently negative slope. And so you would just have an acceleration that looked like that. If you're slowing down, then your velocity time graph looks like this. Slowing down in the positive direction means that your velocity would be going like this. And so your slopes would be these consistently negative slopes. So you'd have a graph that looked like this. Here's those consistently negative slopes, right? And if you're slowing down in the positive direction, your velocity time graph would look like this. Slowing down in the negative direction means that you'd be starting at some negative velocity and approaching 0. And so your slopes would be actually positive slopes. Just graphing the slope. If you were at rest, what does your acceleration look like? Well, if you were at rest, your velocity graph is going to look like this. Right? No velocity here, right? And so you would have slope is 0, right? So we would just show no acceleration. Acceleration versus time is at 0. If you're at rest, you're not accelerating, but we'll actually learn later that it is possible to be at rest and still be changing your direction. To be at rest and changing your direction. So this can also be non-zero in special cases, and I'm just going to write that a little note here, okay? Can be non-zero in special cases. You don't really have to worry about that right now, And then does the slope of an acceleration graph have a meaning? Yeah, it actually does. If you take the slope of an acceleration graph, you get the rate of change of acceleration, which we call jerk. And it's called jerk because if you're moving at different rates of acceleration, you're going to experience a lot of jerkiness and discomfort. So the slope of an acceleration graph is called jerk. All right, so that is motion graphing in 3 different views: position, velocity, and acceleration. Notice how we lose some detail as we take the slope each time, ending with acceleration, which really gives us the least amount of detail.